Hello, I'm Cheryl. In this problem, we're going to find the extreme values of f of xy equals x squared plus 3xy plus y squared with the constraint that x squared plus y squared has to be less than or equal to 1. Now to do this, we're going to split the problem into two cases. The first case is going to be what happens when x squared plus y squared equals 1. So case 1, the constraint is x squared plus y squared equals 1. In the second case, we'll deal with what happens when it's less than 1. So for this first case, I'm going to use the method of Lagrange multipliers. So the first thing I'm going to do is write a function g of xy. So that constraint can be written as x squared plus y squared minus 1. And with Lagrange multipliers, what I'm going to do is I'm going to take the gradient of f of xy and set that equal to lambda times g times the gradient, lambda times the gradient of g of xy. And I also have to know that g of xy is going to equal a constant. So for this problem, what's the gradient of f? Well, the gradient of f is going to be 2x plus 3y times my vector I plus 3x plus 2y times my vector j. And this will equal lambda times the gradient of my function g. So my gradient of my function g is going to be 2x I plus 2y j. This equation turns into 2x plus 3y times vector I plus 3x plus 2y times my vector j. And that's going to equal 2x lambda times I plus 2y lambda times j. All right, now I have two vector functions that are equal to each other, so their components have to be equal. So that tells me that 2x plus 3y and 2x lambda have to be the same thing. So I'll write 2x plus 3y, that has to be equal to 2x lambda, and 3x plus 2y has to be the same thing as 2y lambda. So I have 3x plus 2y equals 2y lambda. And I also have my equation that g of xy has to equal a constant. So I know that x squared plus y squared minus 1 is equal to 0. And now I have an equation, three equations with three unknowns. So I can solve the system of equations. I'll begin by looking at these first two. And I'm going to go ahead and solve each of them for lambda. So in the first one, I'm going to have 2x plus 3y all over 2x equals lambda. And in the second equation, I have 3x plus 2y all over 2y equals lambda. Combining those together, I notice that 2x plus 3y all over 2x has to equal 3x plus 2y all over 2y, because they're both lambda, so I set each of them equal to each other. Okay, so I'll go ahead and do some cross multiplying here. I've got 2y times the quantity 2x plus 3y equals 2x times the quantity 3x plus 2y. That leaves me with 4xy plus 6y squared equals 6x squared plus 4xy, which leaves me with 6y squared equals 6x squared, or in other words, y squared equals x squared. So y could be plus or minus x. All right. The next thing I need to do is take this result and plug it into my third equation. So I'm going to have x squared plus y squared minus 1 equals 0. And I know that y squared and x squared are the same thing. So I have x squared plus x squared minus 1 equals 0, or 2x squared equals 1. X squared is 1/2, so x could be plus or minus 1 over the square root of 2. Now, if x is 1 over the square root of 2, I know that y will also be plus or minus 1 over the square root of 2. So y equals plus or minus 1 over the square root of 2. So I have 4 different points that I need to consider here. So what I'm going to do is I'm going to plug each of those 4 points into my original problem. So if I take f of 1 over root 2 and 1 over root 2, where they're both positive, and I plug that into my original problem, I'm going to have 1 over root 2 squared plus 3 times 1 over root 2 times 1 over root 2 plus 1 over root 2 squared. And if I do the calculation, this turns out to be 5/2. Now I'll try f of 1 over root 2 and minus 1 over root 2. Again, I'm just plugging it into the original function f. When I do that, I end up with a negative 1/2. If I try f of minus 1 over root 2, 1 over root 2, again, just plugging this into the original function, I'm going to end up with a negative 1/2. And finally, my 4th point will be what happens when they're both negative, minus 1 over root 2 and minus 1 over root 2. Again, plugging that into the original function, I get 5/2. So if I'm only looking at the constraint, x squared plus y squared equals 1, it's looking like my maximum is going to be 5/2 and my minimum is going to be negative 1/2. However, now I have to do the second case where I test to see what happens when x squared plus y squared is less than 1. So we're going to clear the board to make some space to consider what happens in that case. Now let's consider what happens when x squared plus y squared is less than 1. So for case 2, x squared plus y squared is strictly less than 1. That's inside of our circle. So in order to find any relative extrema inside that circle, I'm going to go ahead and find critical numbers. So I'm going to look for the partial of f with respect to x, which is going to be 2x plus 3y. And the partial with respect to y, xy, is going to be 3x plus 2y. Now I know that critical numbers will exist when either one of these partials is undefined or when they're simultaneously equal to 0. So let's go ahead and set them both equal to 0. So 2x plus 3y equals 0, and 3x plus 2y equals 0. So to solve this system, let's take the first equation and multiply both sides by negative 3. And the second equation will multiply by positive 2. So I have negative 6x minus 9y equals 0, and 6x plus 4y equals 0. This is going to lead to a minus 5y equals 0, and y equals 0. Substituting y equals 0 into one of my original equations, I'll have 2x plus 3 times 0 equals 0, which means that 2x equals 0 and x equals 0. So that tells me I have a critical point at the point 0, 0. All right, now, is this critical point a minimum, a maximum, or neither? Well, if you remember, we have the second partials test that will help me with that. So what I need to do is to look at the second partial at the point 0, 0, multiplied by the second partial of y at the point 0, 0, and then subtract the mixed partial at the point 0, 0 squared. All right, so what's the second partial of f with respect to x? Well, here's my first partial. My second partial with respect to x is just going to be 2. And it's going to be 2 no matter what the input value is. So at 0, 0, that second partial is a 2. My second partial with respect to y is also a 2 at any point. So this value is also a 2. I now need to calculate the mixed partial. So I'll go back here to my partial with respect to x, and I'll differentiate with respect to y. That's going to give me a 3. And again, I'm interested in what happens at the point 0, 0, but it's always equal to 3. So that'll be a 3, and it's squared. So this is going to be 4 minus 9, which is a negative 5. Now, this value is definitely less than 0, which means there's not a minimum or maximum at 0, 0. This is a saddle point. So there's a saddle point at the point 0, 0. So that does not lead me to any extrema at all. So now I have to put both of my cases together. I didn't get any extrema for my second case, but in my first case, I did get some extremas. So I know that 5/2 is the maximum value and minus 1/2 is the minimum value. I hope that was helpful. Thanks.